when we start with trig, we limit it to right angle triangles. But of course, angles don't stop at 90 degrees. So how do we deal with angles of any size or any magnitude? So how do we deal with it? Well, there's my number plane. We imagine the unit circle. I suppose it doesn't have to be a unit circle, it's just a circle. When we start naming, over here on the positive x-axis, we tend to always measure to the positive x-axis. I don't know if you've noticed that or not, but we often refer to the positive side of the x-axis when we deal with things. So we start there at 0, so then obviously 90 is at the top of the y-axis and so on all the way around till we get back to 360, and we can keep going round and round and round. So as we start at 0 and go to 90, that becomes our first quadrant where everything's positive. Second quadrant over here where x is negative, y is positive, and so on and so on. I've drawn in, well, what I like to call the butterfly. It sort of looks like a butterfly. What it basically is 4 right angle triangles. So we can convert any angle back to a particular right angle triangle. The acute angle that we're going to be interested in, again, is the angle it makes with the x-axis. So it's always the angle it makes with the x-axis in the different quadrants. So in the first quadrant, all the angles are between 0 and 90, everything's normal, not an issue. Our second quadrant, the quadrant I like to call 180 minus theta. Theta is the acute angle we're interested in, but the actual size of the angle would be 180 minus whatever that acute angle is. Because we would start at 0, go around to the green line, so we're at 180 minus the theta. Now in that quadrant, if you imagine that right angle triangle there, the x value is negative, the y value is positive, hypotenuse is a distance, so we always assume that to be positive. So sine is opposite over hypotenuse, so we get a positive number over a positive number, sine ends up being positive. Cosine, we get a negative number over a positive number, so we end up with a negative, and tan, opposite is positive, adjacent is negative, and so we end up with a negative number in the second quadrant. So I don't know whether that has actually been explained to you before, but that is why sine's positive in the second quadrant, but the other two are negative. And we can do that in each of the quadrants. The third quadrant would now become 180 plus whatever the acute angle is. And now in the third quadrant, the x value is negative, but the y value is negative as well. So sine becomes negative on positive, negative. Cosine is also negative on positive, negative. The tan ratio, though, will be negative on negative, so that's why tan's positive in the third quadrant. And then we go over to the fourth quadrant, which would be 360 minus the acute angle. And now the x value is positive and the y value is negative. So sine, negative over positive. Cosine, positive over positive. Tan, negative over positive. That explains why cosine is positive in the fourth quadrant. And there's all sorts of ways of remembering it. Some people remember it as all stations to central, or ASTC, or different ways. You've got calculators, of course, but before calculators, what we used to deal with was these mathematical tables, like we have on the poster over there. And we would have a table for each of the ratios, but they would only go from 0 to 90 degrees. So if I wanted to find out the sine of 260, what I would have to say is, well, 260 degrees, which quadrant's that in? That's in the third quadrant. I know sine is negative, but what would the acute angle be? Now the third quadrant is 180 plus the acute angle. So 180 plus what gives me 260? 80. So I'd go to the table, I'd look up whatever the sine of 80 is, and it would be negative of that number, so negative 0.9848. So you've got calculators these days, but if you entered sine of 80 and sine of 260, you'll notice that, oh yeah, that's the same number, but one's negative, one's positive. So tan of 220, once again, we say, oh well, yeah, third quadrant, tan's positive. 180 plus what gives me 220? 40. So it'd be the same as tan 40. Look that up. 0.8391. We didn't have tables for secant, just like you don't have a button on your calculator for secant. But secant is the reciprocal of cosine, yeah. Now 105 is in the second quadrant. Cosine is negative in the second quadrant, so therefore its reciprocal should be negative as well. We don't change the sign, we're just turning it upside down. So yes, it would be negative. The acute angle, second quadrant, 180 minus what gives me 105? 75 degrees. So then I would have to look up the cosine of 75 degrees, and then I would have to go, well, 1 divided by that, what's that equal? And it turns out to be minus 3.8637. Now, I guess you would have to do a similar thing, because again, no secant button on your calculator. You'd find the cosine of 75, but you also have a reciprocal button on your calculator you can press and turn that answer upside down. We'd go, I can't find the secant of 105, so I'll find the cosine of 105, work out what that is, then hit your reciprocal button, and hopefully it'll come up as negative 3.8637. Of course, we don't have to stop up at 360 degrees because you keep going round and round and round and round and round. So if it's more than 360, you just keep subtracting 360 until we've got an angle we can handle. And in this case, I get an acute one straight away. So 70 degrees, first quadrant, everything's normal. So cos 70.3420. And in fact, you don't have to go around anti-clockwise. If you go around clockwise, we just make the angle negative. So a negative angle just means I'm rotating in the opposite direction. I'm going clockwise instead of anti-clockwise. So the tan of negative 67, how do I deal with it? There's different ways I could do it. Again, I'll just use the idea of 360. I can add and subtract 360 and I'll still be in the same position. So if I add 360, I get 293. Well, that's in between 0 and 360. 293 is in the, so our fourth quadrant. Kind of makes sense when you think about it, because I've only gone 67 degrees in the opposite direction. The acute angle would be 360 minus what is 293. So it's negative. So this is the other way I could have done it. Do you remember what the tan curve looks like? It has rotational symmetry. It's an odd function. Remember the definition for an odd function. Function negative x is equal to the negative of function x, and that's what I've ended up with. Tan of negative 67 is the negative of tan 67. So that's another way I could have done the question. I could have used the feature of it being an odd function. However we decide to do it, negative 2.3559 is our answer. Okay, I've got this point on a circle, radius is 5 units, I know that angle is 30, it wants me to find the coordinates. Well, I can create a right angled triangle there. X over 5 is cosine 30. Cosine 30 is one of our exact values, which is?
3 on 2.
Oh, very swift, well done. So we get 5 root 3 on 2. Y over 5 is sine 30. 5 sine 30, sine 30 is? 5 on 2. That's not the answer in this case because they've asked for the coordinates, so I should answer it as coordinates. So P is that particular point. But what happens on the actual boundaries themselves? So 0, 90, 180, 270 and so on. What I tend to look at first of all is a triangle. It's a fictitious triangle because the size of the angle in the triangle is 0 degrees. So by angle sum of the triangle, the other angle is 90. Okay. The length of my base is 1. Now think about this. If my base is 1 and I haven't gone up any height because it's 0 degrees, the opposite must be 0. And by Pythagoras' theorem, the other side is 1. Okay, now I can read off my boundary values. So 0, sine of 0, opposite over hypotenuse is 0, cos of 0, 1 over 1, that's 1, tan of 0, 0 over 1, that's also 0. 90 degrees, we get 1, 0. Oh, look at tan 90. 1 over 0. We have an issue. And if you think back to the graph again, that's where we had our vertical asymptote. Doesn't exist tan 90, so it's undefined. Okay, well, how do I work out 180 then? Well, 180, sine of 180. I could say 180. It's either in the second quadrant or the third quadrant. Which quadrant do you want it to be in?
Third.
Okay. Sine, positive or negative?
Positive.
That's right, negative. Well done. And the third quadrant was 180 plus theta. So 180 plus what gives me 180?
0.
So therefore it's the same as the negative of sine 0. Oh, well, sine 0 was 0. Negative 0 is 0. Sine 180 is 0. Okay. Cos 180, which quadrant do you want it to be in? Second or third?
Third.
Okay, again, we'll say third. Cosine, positive or negative?
Positive.
That's right, negative. You're on fire today. Ad for being on time, right there. Now, so we know it's negative. Third quadrant, 180 plus what gives me 180?
0.
Cos of 0 is 1, so this one is negative 1. And then we get tan 180, second or third quadrant. Hang on, ready? Shh, no one else answer.
Positive.
Oh, well done. Okay. Tan is positive in the third quadrant. So it will be the same as tan 0, which is 0. And then I can do a similar thing for 270. We end up with negative 1, 0. Well, negative undefined. Well, it's still undefined. And 360, of course, you're back at 0. Now, that's how I used to do it. Reality is you've got a calculator. Have a look at all those numbers. So the 1, 0, or error. So if you're ever unsure, you just go to your calculator. Oh, sine 0. What's that? Oh, 0. Fantastic. Okay, so no big deal there with our boundary values. But they do become very important when it comes to the curve sketching, that we know what those boundary values are. So let's have a look at the basic trig graphs. Let's say the easiest way to draw a trig graph is to plot those boundary values. So let's have a look at sine x. We know the sine curve goes between -1 and 1. That's its amplitude. So I've labelled that on the y-axis. I've labelled every 90 degrees. They were the boundary values. And I've got a little bit carried away. I've gone all the way up to 720 and back to -360. So when I draw a trig graph, I'm going to draw a sine. I ask myself, where does it start? What is the sine of 0? So I plot that point in. Then I go to 90. Sine 90 is? Plot that point in. But then I know this pattern continues. So I'm up at the peak. I then must come down, and then down, up, down, up, down. Then I'll go back the other way. And then we draw it in. Now it's not like back when you're in kindy and doing dot to dot. And you go, oh, nice straight lines, fantastic. Remember, it's a nice curve that goes through them all. And so there's y equals sine x. Now, just by looking at that, we can tell a few things. Domain, there's no break in the curve whatsoever. All real x. I can put any number in and get an answer. Range, so it goes between -1 and 1. Period. Now, the period is how long till it repeats. But repeats identically. So it's tempting to go, oh, look, at 0, I'm at 0. 180, I'm back at 0. So the period's 180, but that's not true. Because at 0, my curve is going up. But 180, my curve is going down. It's not until I get to 360 that I'm at 0 and going up again. So it's how long till it repeats the pattern. So 360 degrees, say it's an odd function, so that means the sine of negative x will always equal the negative of sine x. And that might come in handy for some questions. So we can get rid of the negative angle by turning it into a negative sine of the positive angle. Okay, cosine graph. What are we expecting? I mean, I know you know what it looks like anyway, but let's pretend we don't. What are you expecting to see? Because remember, what did the co stand for? Complementary. Angles add up to 90. So I should see the same graph, but what happens to it? Yeah, I should shift 90. shift 90 degrees. Well, let's see. Plotting the x values. This time I'm starting at 1. Cosine graph, cosine 0 is 1. So I start up the top, then I go down, and then that pattern repeats, down and up, back of the negatives, and draw that in, and sure enough, it's the sine graph shifted 90 degrees to the left. And that's because they are complementary ratios. So they're the exact same graph, just changed. Let's look at the important features we can get from our graph. Because they are the same graph, we should see the same things happening. The domain is all real x. The range is between -1 and 1. The period is 360. However, look at the picture. It is not an odd function. However, it is an even function now. Because if you look at the y-axis, you've got symmetry there. You could fold that on top of itself. So even function, which means if we wanted to get rid of the negative with cosine, cosine negative x will equal the cosine of x. Alright, we can't complete it without tan. You'll notice I didn't bother labelling anything on the y-axis because our tan curve, it goes all the way from -infinity up to infinity. It doesn't turn. So we go 0. Tan starts at 0, but then it's undefined. So I'll put in a vertical asymptote. Then that pattern just continues. 0, asymptote, 0, asymptote, 0, asymptote, 0, asymptote, 0, asymptote, 0. So where do we go? We know we're going to bend towards the asymptotes, but I got a couple of possibilities there. But I know that in the first quadrant, between 0 and 90, tan is positive. So I know I'm up here. The fourth quadrant, which would be 0 to -90, tan is negative. So my curve does that. Now, when you are drawing your tan curve, be careful because the temptation is to draw it like a cubic, and a lot of people do that. But it cuts through at 45 degrees. It's not horizontal like the cubic. Okay? So it cuts through at 45 degrees. The reason why it cuts through at 45 degrees, does anyone know that? Tan 45 is 1. Okay. What else is 1? The slope of the line y equals x is also 1.
Tan theta is the gradient.
Tan is the gradient. You might remember that from coordinate geometry. We'll see that again later this year, but tan is the gradient. So it all ties together nicely. And then that pattern repeats in each of those little branches. You'll notice to write the domain I need a bit more room because we've got all those asymptotes. It's very hard to write down all real x except 90 or 270 and so on and so on and so on and so on. So I just come up with a generalization there. I'm saying 90, but then every 180 degrees before that and after that we'll have an asymptote. So I've just said plus 180k, where k would be some whole number. So every multiple of 180 we'd find an asymptote. Range is easier because it's just all real y. There are no breaks. Vertically,
It's 180.
yeah, it's only 180 for a tan curve. So period 180, it is an odd function, so therefore tan negative x is equal to the negative tan of x. Oh, so what's this graph I'm going to draw?
Cosec.
Yeah, that's not fair. You looked at the sheet. That's called cheating. Okay, cosec. Cosec is the reciprocal of... So basically, I draw a reciprocal graph like we did before. So it's the reciprocal of sine. There's my construction graph. What did we say with reciprocals? Everywhere there was an x-intercept, it becomes... So let's make those all asymptotes. 1 was a key number. Turn 1 upside down, you get 1. Each of those peaks are at 1 or at -1. So they will stay there. Everywhere it's below, goes above. Everywhere it's above, goes below. So we get a series of these U sort of shapes bending towards the asymptotes. So there's our cosec graph. Okay, ooh, that was a long one. How long was that, you reckon?